Okay, today we're going to be going over analyzing lines of fit. Okay. In this section, we're actually mainly going to be dealing with scatter plots and determining the equation of best fit, or the line of best fit equation or prediction equation. And also, we're going to be talking about the correlation coefficients when it comes to scatter plots. So jumping into the first one here, find the line of best fit. This table shows the world population. Identify independent and dependent variables, make a scatter plot, and determine the relationship, aka make the equation of the data. All right, independent and dependent variables. The dependent variables are going to depend, key word there, on the independent variables. So independent is what we are given, and dependent usually means what we're going to have to calculate. Okay, and for the majority of the time, independent variables are going to be our x column, while the dependent is going to be our y column, because we are going to have to compute what these values are over here. Okay, because for given in year 1650, there's some sort of equation we can use to get this value. So the population depends on what year it is. That's why we get the y value here being our dependent variables. Now the scatter plot we're going to make on the Desmos calculator. Okay, so we won't really see that too much here, but what mainly we're going to be focused on is using the Desmos calculator to get the equation. Okay, now just as a side note here, keep in mind y and f of x are the same thing here. Y, we just mainly deal with linear functions, which we are going to be talking about some lines of best fit equations, which are linear. But we want to go ahead and start switching to f of x just to help us out for future functions and for the next example here. Okay, so we are going to be looking for the equation f of x is equal to mx plus b. Okay, in which case we need to find the m and we need to find the b values in these given examples. Now, in order to calculate that, we got to get on the Desmos, put this table in, and don't forget, main equation we need to hopefully keep converting to memory. Y1 squiggly, mx1 plus b. Okay? Once again, all we have to do is put in table. The second thing is the equation here, and all the third thing we're going to be looking for is the m's and the b's here, okay? So we're mainly going to be looking for. So when we input this information into the Desmos calculator, if you want to try to go ahead and do that, input this in as a table, and then the second equation, we want to go and put the y1 squiggly mx1 plus b, and see if you can't find the m and the b there. So if you want to pause the video and do that, you can. Okay, when we plugged in our table here into our Desmos calculator and then had our equation, we found that we had an m value of 13.67, and then we did have a little bit of rounding here, so 678, and then the y-intercept ended up being negative 22,958.6. Okay, all we have to do from here, guys, is just plug in our slope and our y-intercept into our equation. So our prediction equation of this line of best fit here is going to be, instead of mx, it'll be 13.678x. Instead of plus b, it's going to be minus 22,958.6. And this would be our prediction equation, or our equation of line of best fit for the given set of data points here. Okay, all we have to do was use the Desmos calculator to plug in the table, use our equation y1 squiggly mx1 plus b, and we were given the slope and the y-intercept that we could use to plug in. Now the next example here, we're going to be still using these three steps here, but they do add an additional step at the end, so let's see what we have here. The table shows the approximate percent of students who sent applications to 2 colleges in various years since 1980, supposed to say 5 there, but it's written as 1985 down here. So write a prediction equation, which is what we did in the last example, but then determine how many students will apply to 2 colleges by 2021. So we want to do the same thing we did in the previous example. Plug in our table, use the equation y1 squiggly mx1 plus b, find our slope and our y-intercept, and make a prediction equation. So if you want to pause the video and try that, you can. Okay, now once again, we got to be figuring out what our slope and our y-intercept here is. When we plugged in these points and used that equation, we ended up getting a slope of negative 0.448 and got a y-intercept of 907.714. Once again, we're going to have to plug that into our equation here. F of x is equal to mx plus b. And we're going to end up with f of x is equal to negative 0.448x plus 907.714. So that ends up being part of our answer right there. Now, there was a second part. They wanted us to predict how many percentage of students will be applying to 2 colleges in the year 2021. So that just means we got to take our prediction equation here and plug and use the year 2021. So that means we're going to end up with negative 0.448 times 2021 plus 714. Well, again, we'll do this. We evaluate over here on the right side. So when I get the function at the year 2021, we ended up with 2.306. Okay. So what this is saying here is, according to these data points, and the prediction for us here in the year 2021 is that if this trend continues, 2.306% of students will be applying to only 2 colleges. Okay. All right, now we're going to move on to talking about correlation coefficients. Okay, correlation coefficients. Excuse me. All right, correlation coefficients calculate the strength of relationship between the relative movements of 2 variables, which for what we're dealing with here is the movements between the x and the y variables. The values range, okay, from -1 to 0, or sorry, -1 to 1, in which case -1 is a perfect negative correlation, while +1 is a perfect positive correlation. And we talked a little bit last week about when we end up with the R value. Once again, remember that's what we're dealing with here, the R value. After, like in the examples that we just previously had, we had R and R squared. This is the R value. When we end up with 1 and -1, we end up with linear functions. That means all the points fall onto one line. We have a linear function. Now, we did have some examples where we had like 0.984s and 0.742s or something like that, or -0.664s, okay? Those are going to have different types of correlations, okay? The closer, this is what the third part here is, the closer that when we put in a set of data points, that the number is the closer it is to 1 and -1, for instance, something like 0.954, the more it resembles a linear function. Now, the closer that our correlation coefficient is closer to 0, that means we have what we resemble as a node trend scatter plot, where we just have basically points all over the place, and really none of the points are close to our linear or to our line of best fit. So we do have 3 examples here. I'm going to leave the 4th one open for you guys to try on your own. But here's what we need to do for these examples, and it's actually very similar to what we did on the previous one. We have a table here. We need to, once again, just like we did before, input the table, type the equation y1 squiggly mx1 plus b, okay? But this time, instead of looking for the slope and the y-intercept, we're only going to be looking for that R value, okay? So when we plug these points into our table, and then we put it on our equation, we should get our R value for this given one. So if you want to pause the video and try any of these 3 right now, you can. Okay, when we input this table and then input our equation, we do get an R value here. We are going to round. So we are doing approximations here. Round to the nearest thousandth, we end up with 0.969 for this first one. So that number is pretty close to 1, which means these points almost fall on a linear line. Okay, but we will have some ones that are maybe even 0.99 something. So that means they're really close, maybe 1 or 2 point off. Okay. Because remember, the closer this is to 1 or -1, the more our graph is going to resemble a linear function. Now, if we go for this next one here, we just basically take out the table on Desmos and put this one in. We can go ahead and leave in the equation. If we try to put it in this table, we're going to end up with 0.754. Okay, so once again, still a positive correlation because it's a positive number. Okay, and if we notice here in these 2 graphs, our graphs have been going. I mean, it's hard to tell, but especially when we put in our table and our function here, we've been noticing that we've had a positive slope for the line of best fit. Okay, that's why these are positive. The next one here, if we take a look at the y values, how they're going down, probably going to end up with a negative slope there and negative correlation coefficients. Okay, so in this one here, we notice that it's not as linear as this one, but it still resembles something linear. Okay, Now we do notice that this point on the, when we graph these points is pretty far off from the rest of them, because the rest of them look to be kind of linear, and then this one being far away from the line kind of throws it off. Remember, that is the outlier, okay? The outlier. Okay, we might have a point that's really far off, and actually if we took this point out, I believe this value ends up going from 0.754 to 0.95, okay? So it does have a dramatic effect on our function here, but once again, it's still one of the points we have in here, so that's why we want to include it in here. Okay, if we were to input this table in, once again, since we saw that the y's are going down, we should end up with a negative, and we do. We end up actually with negative 0.942. So a pretty strong linear function here almost, okay? You know, not as strong as the first one that we had, but it's still pretty, it still resembles like they're trending towards a linear function, even though they are not. Once again, you want to try this on your own, think of a random set of points. Doesn't matter how many. Well, definitely, I would definitely do more than 3, because if you have just 2, you know, 2 points determine a line. So if you want to have 3 or more points, maybe something like 7 or 10 points, whatever, test it out, see what happens on your own. All right, this last one's example number 4. Apologies for the misprint there. Now, what this one is doing, it gives us a table, and then it gives us a prediction equation someone else has made. We need to check, 1, if this is the correct prediction equation for this table, and if it is, we're done. But if it's not the correct prediction equation, we need to create the correct prediction equation. So, same thing here as before. We got to input the table. We got to use y1 squiggly mx1 plus b. Okay? 3, check to see if it's the same thing as that one. No? We need to create. We need to find the slope and the y-intercept to create our own equation. Once again, input the table, use our equation, check to see if the slope and the y-intercept match. If they do, we're done. If not, use the y-intercept and the slope to create our new equation. You can pause the video and try this on your own if you want. Okay. When we input this table here, we do not get the slope and the y-intercept that they have in here, even if one of them matched up. Both of them need to work. Okay. So this one's not correct. Okay. Not the correct prediction equation. So we need to calculate our prediction equation. Okay. Now, when we plotted these points and used our equation, the slope that we got was negative 0.487, and the y-intercept was 6.045. Once again, as we've done before, we're going to plug that into f of x here. So f of x, mx plus b. All right. Plug our slope, plug our y-intercept. End up with f of x is equal to negative 0.487 x plus 6.045. The y-intercept was pretty close to the prediction one, but the slope definitely was not close. Now, some other questions they could ask from us in this one, they might say, all right, what's the prediction that x is equal to 30? In which case, we would just plug in 30 everywhere we see an x and evaluate. They might also ask for the correlation coefficient in this one, in which case we could just state it. And by just looking at the numbers and looking at the slope, looks like we would end up with a negative correlation here, okay? All right, that is going to conclude the notes over this section. Make sure we're staying on top of the assignments. And as always, if you have any questions, especially not being able to see Desmos on this one, if you do have any questions and want to see how we go about looking for these values and everything, make sure you come in, find the time to come in and see me. But if you have any questions beyond that, send me an email.